Hello friends, I welcome you in lecture number 36 on relations. In this lecture we are going to discuss about converse of an equivalence relation. We will prove that if we have an equivalence relation, then its converse is also an equivalence relation. And before proving this result, we just recall the definition of converse of a relation. Suppose R is a relation on a set X, that is R is a subset of X cross X, then converse of R is denoted by this notation R tilde or R inverse and is defined as the set of all ordered pairs BA such that ordered pair AB is member of relation R. In short, converse of relation R is obtained by interchanging the order of components in each ordered pair of the given relation. If we are changing the order in each ordered pair of given relation and then we write down all those ordered pairs in one set, then that set is nothing but converse of a relation. So we have whenever ordered pair AB is in R, then ordered pair BA is in R tilde or R inverse, and equivalently it is true on both the sides. If A is related to B by relation R, then B is related to A by relation R tilde. So remember that converse of relation is obtained by reversing the order in each ordered pair of the given relation. Now here we are given that R is an equivalence relation on a set A, and we have to prove that the converse of R is also an equivalence relation on a set A. That means we have to prove that converse of R is reflexive, symmetric and antisymmetric, provided that R is reflexive, symmetric and transitive, not antisymmetric. We know that an equivalence relation is that relation which is reflexive, symmetric and transitive. So first we prove that converse of R is reflexive. So for that we have to prove that for any element in the given set, we have to prove that ordered pair A comma A is in R inverse, or another notation is R tilde. Now we know that R is an equivalence relation, therefore R is reflexive, therefore ordered pair A comma A belongs to R, because R is equivalence relation and therefore R is reflexive. So here I can write that because R is reflexive, for A belongs to capital A, ordered pair A comma A belongs to R. Now by the definition of converse of a relation, if we interchange the order of components here, then we will get the same order pair because both the components are equal. Therefore by the definition we can write that this is in the converse of R, and therefore we can say that this A is arbitrary element of capital A, and therefore order pair A comma A belongs to R inverse. So I can write that therefore for any A in a given set capital A, ordered pair A comma A belongs to R inverse, and therefore R inverse is reflexive. So this is first property to prove that R inverse is an equivalence relation. Now for second property, we have to show that whenever for two arbitrary elements AB belongs to A, suppose we have two elements AB in capital A, B such that ordered pair AB is in R inverse. Now to prove that R inverse is symmetric, we have to prove that ordered pair B comma A belongs to R inverse. So we assume that suppose ordered pair AB belongs to R inverse, and we try to prove that ordered pair BA is also in R inverse. Now ordered pair AB is in R inverse, therefore by the definition of converse, ordered pair BA belongs to R. This is by the definition of converse of a relation. But we know that R is equivalence relation and therefore R is symmetric. So whenever BA belongs to R, we must have AB belongs to R, because relation R is symmetric. Now AB belongs to R implies BA belongs to R inverse by the definition of converse of a relation. So we have shown that if we take any two elements A, B in a given set A such that AB belongs to R inverse, then BA is also in R inverse. This means R inverse is symmetric. So we have shown that if R is symmetric, then R inverse is also symmetric. Now for transitive property, we consider three arbitrary elements, say A, B, C in capital A, and these elements are in such a way that ordered pair AB belongs to R inverse and ordered pair BC belongs to R inverse, and we want to prove that ordered pair AC belongs to R inverse. If AB belongs to R inverse and BC belongs to R inverse implies AC belongs to R inverse, then R inverse is transitive. So we assume that suppose we have this type of ordered pairs such that second component of this ordered pair is equal to first component of this ordered pair, and if this happens, then we should prove that AC belongs to R inverse. So here also we use the definition of R inverse. AB belongs to R inverse gives me BA belongs to R by the definition of converse. Same thing here, BC belongs to R inverse, that means ordered pair CB belongs to R, and we know that R is transitive because R is an equivalence relation. Now I am writing this ordered pair first. I have C comma B belongs to R, and I am writing this here, ordered pair BA belongs to R. So you can see here second component of this ordered pair is equal to first component of this ordered pair, and R is transitive because R is an equivalence relation, therefore R is transitive, and CB belongs to R and BA belongs to R, or we can say that C is related to B and B is related to A, and R is transitive, therefore we must have C related to A, or ordered pair CA belongs to R. Now by the definition, if ordered pair CA belongs to R, then ordered pair AC belongs to R inverse. Hence we have shown that for ABC belongs to A, whenever AB belongs to R inverse and BC belongs to R inverse, we have ordered pair AC belongs to R inverse. This proves that R inverse is transitive also. So we have proved that R inverse is reflexive, symmetric and transitive. Therefore R inverse is an equivalence relation on a set A if R is an equivalence relation on the same set. If R is an equivalence relation, then R inverse is also an equivalence relation on a set A. So this is very easy to prove that converse of an equivalence relation, another name is inverse of an equivalence relation, is also an equivalence relation on a given set A. So this is all about this session. I hope you like it. Thanks for watching.